We are on lesson 2 of chapter 6, which is volume of prisms and cylinders. First, we're going to find the volume of prisms and cylinders. Then we're going to explore the effects of changing dimensions. Then we're going to find the volume of composite figures. Our new vocab word here is volume. Volume measures the amount of space that an object occupies. And we know that space is in 3 dimensions. It's always a little bit difficult to explain 3 dimensions on a 2-dimensional screen, but if you look at this shape here, it has a length, it has a width, but it also has a height here. And this prism here takes up space in those 3 dimensions. And it's measured in cubic units. So literally think cubes here. So how many cubic inches could you fit inside this rectangular prism? That's how you measure volume. We're going to find that the same formula is used for all the shapes that we're working with today. Triangular prisms, rectangular prisms, and cylinders. And that formula is base times the height. You find the base, and you multiply it times the height. For prisms and cylinders, the base is always going to be facing another base. So if we see this triangle here, it's facing this other triangle perfectly. This rectangles are not. They're leaning against each other. So that's how I know the triangles are the bases here. I can find the area of this triangle, multiply times this height of it, the figure, and that'll be my volume. For rectangular prisms, you actually can use a couple different bases. I'm going to use this nice long flat piece as the base because it's facing the one on the bottom. Then I could find the area of that and multiply times this little height, and that would give me my volume. For cylinders, I can use the circle here. The circle becomes my base. I see that it's matching this circle up here. Then I can multiply that times the height to get my volume. So first let's find the volume of prisms and cylinders. It says find the volume of each figure to the nearest tenth. Use 3.14 for pi. So let's do this first one. A rectangular prism with a base of 2 meters by 5 meters and a height of 7 meters. Remember, the formula is base times height. So first the base is 2 by 5, so 2 times 5 is 10 meters, and that would be times the 7 meter height. So that would be a total of 70 meters. And remember, that's cubic meters. So a cube, that is 1 meter on each side. Now let's solve this one. This is a cylinder, so the base would be the circle, and it gives us the dimensions of this circle in a radius. So the area of this circle, if you remember our last lesson, is radius squared times pi. So radius squared, or 6 squared, is 36. So 36 times 3.14. 36 times 3.14 is 113.04. That's the base. Now we multiply it times the height, so times 15. So 1,695.6. And then that's measured in meters cubed, cubic meters. Now we have this prism. And here's the mistake that many people make. They make this the base here, or this rectangle the base. But clearly there's 2 triangles that are facing each other perfectly, so this is a triangular prism. So let's find the area of this base. This triangle is 4 feet wide, it's 7 feet tall. So remember, the area of a triangle is length times width divided by 2. So 7 times 4 is 28, divided by 2 is 14. So that's the area of the triangle, 14, and then times 11 would give us our volume. So 14 times 11, 154. So that'd be cubic feet, so feet cubed. Just to recap for that, so we found the area of that triangle, which is 7 times 4 divided by 2. Then you multiply it times the height, which gives you this answer. Here we're going to explore the effects of changing dimensions. So this is a cereal box measures 6 inches by 2 inches by 9 inches. Explain whether doubling the length, width, or height of the box would double the amount of cereal the box holds. First, let's find out how much that holds. Let's make this our base, and we'll make this our height. So 6 times 2 is 12 for a base. 12 times 9 is 108. So our volume, 108 inches cubed. What would happen if we doubled the length, or the width, or the height? Let's find out. Let's make this 12. So 12 times 2 would be 24. 24 times 9 equals 216. So doubled length would equal 216 cubic inches. And that looks like this is twice as much as that. So this would double. Let's double the width then. So 6 times 4 times 9. 6 times 4 is 24, and we just did 24 times 9, which is 216. So doubled width would also equal 216 inches cubed. Now let's double the height, see if that does the same exact thing. So the base of 6 times 2 is 12. Then we'd multiply that times 18. 12 times 18 would be 216. So doubled height equals 216 inches cubed. So in this case we would say yes it would. Doubling either the length, width, or height would double the amount of space to fit the cereal in than the normal size. Kind of a neat thought. Now we have this. A can of corn has a radius of 2.5 inches and a height of 4 inches. Explain whether doubling the height of the can would have the same effect as doubling the radius. So first let's find the volume of this can. So if we're going to find the area of the base, which is the circle here, we would do radius squared times pi. So 2.5 times 2.5 is 6.25. Let's do 3.14 for pi. So 19.625. We multiply that times the height then, base times height, that'd be times 4. So it's a 78.5 inches cubed. Let's figure out if doubling that height makes a difference. So the area of the circle would remain the same, but now we multiply this times 8. So 19.625 times 8 would be 157. So doubled equals 157 inches cubed, and that is doubled. So we're seeing a trend here. Let's try the radius. This might be a little bit different. So now that the radius is doubled, that radius is now 5. So 5 squared would be 25. 25 times 3.14 is 78.5. 78.5 times 4 would be 314. So doubled radius equals 314. So this is not the case. And the reason being is that the radius is squared. So you double it, then square it, and that's going to throw everything off. So we notice that changing the height, changing the width, changing the length, those are just fine. But because the radius is squared when you find the area, it's kind of like doubling it twice. So that's why this is 4 times as big as the regular size. So when you change dimensions, most of the time it is a proportional change, but not always as in the case of the radius. Now we can find the volume of composite figures. And this might seem a little intimidating at first, but if we remember just to treat them as separate figures, we can add them together and get the total volume. So first let's do this easier rectangular prism on the bottom. I see that the base on the bottom here is 6 centimeters and then 9 centimeters. So 6 times 9 is 54. So 54 times the height is 5, so times 5 is 270. So 270 for the rectangle. And now let's find the triangular prism. We find the base of the triangle and multiply that times the height. So the triangle is 3 centimeters tall. It's 6 centimeters long because this side matches with that. So 6 times 3. Remember, you divide by 2 because it's a triangle. So that'd be 9 centimeters times the height, which is the same side as this, so times 9. So 9 times 9 equals 81. So 81 equals the triangular prism. If we add these together, 270 plus 81, that would be 351. And we're going to call this centimeters cubed. So if you treat these as separate shapes, find the volume separately and add them together, it makes it a whole lot easier, and you don't need to be so intimidated by these.